that I guess I'm not used to, the kind of politeness you have in New Zealand, because in America, the audience is decreased each time until they end up just talking to 4 or 5 people. But I'll try to make it not so painful. We've been talking about what we're aiming to talk about is the theory that works the best, that we know the physicists like the best, and that deals with a part of nature, and that's quantum electrodynamics, and deals with photons and electrons. Most of the time we've been talking about photons. What we've discussed is that mainly the main idea of the talk is to give you some idea of the kind of framework of ideas which theoretical physics needs in order to describe results of experiments. And I think by this time you'll agree, after 2 lectures, that they're very weird indeed, and quite peculiar and difficult to believe. But I'll just remind you or review for one more time a little bit about what happens with photons. And as we said many times, a few times before, we have a source here and a photomultiplier which makes counts of photons. Even if we have only 1 photon at a time, and if we have more than one way that a thing can happen. And the example I've been making several times is that the light the photon we could imagine could be reflected from 2 different surfaces. If there's more than one possible way that something can happen, the whole structure works as this way. In any situation where you have experiment looking at something microscopic, which of course you have in the end to look at something macroscopic, that is large, and the photomultiplier amplifies up. When you have a system like that, you can't predict exactly what will happen, but only the chance that the system operates, that you find something happen here. And this probability is always given as the square, or the circle if you wish, of a thing called an amplitude. And this amplitude is a kind of absolute square. It's a special kind of it's a square of the length. And the amplitude is nothing but an arrow drawn on a plane. Now, when something can happen in more than one way, the amplitude that it happens is calculated by adding the amplitude for it happening one way plus the amplitude that it happens the other way. And when you square that, you get the probability. In a problem like this, we have found that the circumstances or the probability for this event might depend upon how far apart you put the plates, and you get reflection from a pair of plates which varies with the thickness in that manner. And so, this, in our particular example, I finally found out that that was 16%, and that was 8%. From each surface, there was 4%. Now, if this were a more ordinary thing, like you would expect, in ordinary type of reasoning instead of this esoteric subject of microscopic physics, you would expect that the chance to arrive here could be analyzed by saying, of all of the ones that come down, some bounce from here with a certain probability, and some bounce from here with a certain probability. Let's say 1/5 bounce here, or what do we say, 1/25. And 1/25 here would be 2/25 of them. What we would do would be to add the probabilities. We find out that instead of adding probabilities in such logical circumstances, we add amplitude. In other words, we can sit around and talk about it this way. You say, well, there's a certain, it can go either this way or it can go that way, and we just add the amplitude before we square. But that means that the logic that we can say that it really goes either this way or that way is false. You can't really say that in the common language way, or you're meant to add the probabilities. Because if you were to say it can either go this way, some of them come this way, and some of them come that way, you're at a total loss to understand why, when the thickness is just right, there is none of them come at all. Because if some of them come one way and some of them come in the other way, the fact that they can go both ways surely isn't going to make it that they don't come at all. But that's exactly what does happen. And so the idea to be able to say that it comes either one way or another it requires that you know what you're talking about. You're not talking about ordinary either one or the other, but either one and the other in the sense of adding amplitude. So it's a crazy game. I still find myself saying, well, it comes either one way or the other. But it is not really true that for a given particle which arrives here, you can say that it either came this way or that way. You get the sensible physical idea out of that. As a matter of fact, it's entertaining. The following thing is very interesting. It is possible to put some kind of atoms on the surface here, such that when light bounces off it, they leave some trace that the atom is left in some other state than it was before. So that if it bounced the light from the surface, an atom on that surface would be left in a different state. Likewise, we can put atoms of this kind. It's rather technically difficult with light, but you can do it in many, many analogous experiments in similar situations. Well, imagine we can do that with this. And then we could say, let us bounce the light, and then afterwards look at the atoms and see which ones are excited. What you discover is, if you have enough here, that you don't miss them. If you forget the cases where you missed, that it's either excited here or it is excited there, yes. In other words, it does look like the photon either goes this way or that way. And when you have the atoms here and you count just those cases in which you can find, you see, I'm worried about the cases where you miss them. Forget the cases that you miss them. And take only the cases where either one or the other atom is excited on one or the other sheet, and ask for the probability of arriving here. And you know what you get as a result of as a function of thickness? A completely different result. If you have atoms there that can leave a trail as to whether light was there or not, you get 8% reflection no matter what thickness. In other words, it tricks you. You're only going to be clever. You know that if you have no way to tell from which one it comes, if the light after it bounces off leaves everything the way it was before, then you get this funny interference effect. If, however, you put something here to see if the light bounced here or here, you can tell it bounced one or the other. It tells you, it leaves the atoms excited. But lo, there's no more interference effect. Why? How do we describe that? It's not hard. It's that we changed the problem. The first problem was, given a source here and material here, what is the probability that for the following event, that the photomultiplier goes off and that the system is left exactly as it was before, that nothing is changed in the glass? That's that curve, the first one. But in the second experiment, we're asking for a different final problem. We're asking a different problem. The problem is, what is the chance, if we have a source here and these layers here, that the photomultiplier goes off and one of these atoms on this layer here, say, is excited? That's a different problem, has a different amplitude. And that has nothing to do with what happens down here. And that amplitude is 4%, or 0.2 rather. Squared is 4%. It has some darn angle, I don't understand angle. Squared is 4%, and the probability that it's reflected from the front surface as detected by an atom there is 4%. Likewise, if you ask for the following situation, that the photomultiplier should go off and the bottom one should have an atom excited, you get also 4%. So you see, if we try to test whether or not it's going one way or the other, then the results of the experiment are changed, or another way, we have to ask about a different experiment. The case of interference is this, that it is such a situation that the rest of the system, the glass, is exactly the same before and after, and there's no way to tell where the light bounced. Otherwise, if you had some way to tell, you'd ask for a different physical result, have a different amplitude and different results. Which means these things I point out because as you've gone along, you've probably struggled to find some kind of a simple-minded explanation of these things. But when you see how annoyingly complicated it gets, I mean not complicated, but curious it gets harder and harder to make a simple model. So we've given up on that. I also emphasized last time that you can get some that one of the things I wanted to emphasize is that things that are very common and observed all the time and which are perfectly obvious are quite different in this world. It turns out that what we thought was obvious is quite wrong, and it's much more complicated. Or not more complicated, but just different. In fact, it's sometimes simpler and more beautiful. A particular example we had was that light was reflected by a mirror at equal angles, or that light went in a straight line, and we demonstrated that mysteriously enough, was the consequence of light going every which way and not necessarily in a straight line. In particular, I pointed out that if we had a mirror which was made of little pieces of the right spacing and had light coming down this way, it's reflected back that way sometimes, but it has a good probability to be reflected at a special angle. That's crazy. That depends on the spacing here. I have been using light, and we've been using red and blue light. When we change the color of the light, this distance changes, but I have explained in the first lecture that the range of conditions is enormous, and that we can have distances corresponding to hundreds of meters for radio waves, and distances corresponding to spacing between atoms, or even much smaller for other rays. In fact, if these little spots were, instead of mirror pieces, just atoms, which are much closer together, very close together, then it's possible to find photons of such short wavelength, much smaller than light. This distance is about 10,000 atoms, the thickness there, but here 1 atom. And when you have light of the wavelength of 1 atom, that's called X-rays. And when you shine X-rays on a crystal, which is where all the atoms organize this nice pattern, say a crystal of nickel or some other metal, you'll find X-rays coming off at special angles. That was discovered in 1914 and was the proof, they said, that X-rays were waves, but at the time all the other evidence indicated X-rays were particles, and we now know, you all know about this puzzle. At the same time, this was very exciting because it not only determined the wavelength, so to speak, for X-rays, it showed they were the same as light, but much smaller wavelength, but also much quicker variation in time of the amplitude. The amplitude changes slowly with red, faster with blue, super fast with X-rays, super fast with gamma rays, and so on. And not only did that, but by the way, incidentally, by measuring these angles, you could determine the spacing and arrangement of the atoms in crystals. And that's how we've gotten to understand how the atoms are packed in various kinds of substances and so on, which is exciting and interesting all by itself. But I'm wasting time because the lecture's on electrons, and I've been talking about photons. But what I wanted to emphasize was the structure. The structure is amplitudes. We get to talk about them all the time. Only later at the end we square them to find probabilities. Amplitudes add when you have different possibilities. We also taught that amplitudes will multiply when the things happen in succession. In fact, amplitudes multiply just like probabilities multiply, and under the same circumstances. If you had, we could analyze this another way. We can say there's a certain, if this were really a chance thing, we say there's a chance it gets from here to here, and a chance it bounces off, and a chance it gets from here to here. It turns out that that's right. You can analyze the amplitudes the same way. There's an amplitude to go from here to here, an amplitude to be reflected, and an amplitude to go from there to there, and you multiply them all together, just like you multiply probabilities. Multiplying, I explained last time, multiplying 2 arrows is done in the following magical way. You have 2 arrows, and you make a new arrow whose length is the product of the lengths of these 2, and whose angle from horizontal is the sum of these 2 angles. So in this case, the product, I don't know what the unit, let's say the unit is this big. The product is a small arrow at an angle something like this. This is the sum of the 2. Anyway, we find we can add and multiply arrows. The mathematicians call them amplitudes, and mathematicians call them complex numbers, and that's the structure of the world. Electrons were discovered in about 1895 or so as particles, and they were studied and believed to be particles. They behave very much like particles. You could count them. You could put one of them on an oil drop and measure the electrical charge. Electrons responded to the presence of other electrons. If you had a metal plate here and a metal plate here and had an excess of electrons here and a defect so that what's left over is protons here, then an electron sailing through between the plates would be repelled from the other electrons and attracted to the proton and move in a curve something like this. Millions of electrons moving through a wire represent an electric current, and so on, and so on. And the entire picture of electrons as particles going around in matter explained many phenomena, and everything was going along all right. There was some puzzles about how they behaved in an atom. If you've heard about the atom as being a little solar system with a nucleus in the center like the sun and the planets going around like electrons, then you're back in 1900 and something, 1910 or so, because it's quantum mechanical, as it turned out. By 1923, de Broglie suggested that this business about mixture, this wave and particle properties like light, was probably also true of electrons. And no, historically, the wave aspect, aside from Newton's era, the wave aspect of light was most obvious, and the particle aspect was discovered afterwards. In the case of electrons, the particle aspect was most obvious, and the wave aspect was discovered afterwards. By almost in 1924, only a short time after de Broglie's suggestion, Davison and Germer was doing some experiments bouncing electrons off of nickel, expecting them to bounce back this way, which they did. But they also discovered that some of the electrons went off on a crazy angle. And when they read de Broglie's paper, I can't pronounce it. Sometimes they call it de Broglie, and sometimes de Broglie, and sometimes de Broglie. It's a French name, so it's hopeless. And they found that these electrons came off at an angle, and that they calculated the angle, what the wavelength had to be, because you know the spacing of that from the experiments with X-rays. They found out that that was exactly right, according to de Broglie's theory, and that electrons, in fact, did the same thing as light in the same kind of dual hocus-pocus. In translating the words dual hocus-pocus into better English or better physics, it's this: that even an experiment involving electrons going from one source, say a tungsten filament, to a counter of some kind, is exactly analogous to the situation with light. In fact, all of physics, as it turns out, as far as we can tell, is all the same framework. There's a probability for an event, and the probability is the square of an amplitude. And there's an amplitude that an electron goes from place to place. The amplitudes can be compounded by addition when there's more than one way to happen, and by multiplication when you can think of things happening in succession. That means that all the possible events in the world that might be analyzable into separate, simple events of which everything is a compound. For instance, is it possible to describe like everything that happens as a series of events? For instance, it jumps, it goes from here to here, it bounces off, it goes from here to here, and so on. I'll give a specific instance in a minute. What does turn out to be true, and this is what the content of the present lecture, is I want to start all over again and tell you, now that I've introduced and I've convinced you about the framework of probability amplitudes, I must give you the laws for the probability amplitudes, and that way give you the complete theory of quantum electrodynamics. It turns out there are only 3 laws, okay? But they have to do with the idea an amplitude that an photon goes from place to place, an amplitude that an electron goes from place to place, and an amplitude that an electron emits a photon. I'll describe them in detail now. Now I want to give a more complete description of the way the laws of physics look, at least in this partial realm involving only electrons and photons. In order to give this description, I have to include something which I didn't include before, for simplicity. I include now the time. In the experiment which, here it is. In the experiment which I thought I had just erased but didn't, we can ask another question. We can ask, if the source is made to emit a photon at a given moment, what is the probability that the counter receives a count or goes off at a given moment? This adds the idea of time to the things that we've been doing before. We can ask a question that's, in other words, more complete, not only where the thing is and at what time it arrives. And so we have the following world. We have an amplitude inside of space-time, space and time. Things move around in space, and they take time to do so. They don't really move. They have amplitudes for doing their thing, okay? But their thing is done in space and time. You can ask for the amplitude that a photon arrives here at a certain time and an electron is somewhere else at another time, and so forth. Now, in order to describe both the space and the time pictures, I'm going to make a kind of graph which we call, which is very handy. If I call it by its name, you'll be frightened. So I'm not going to call it by its name. I plot the position in space sideways here and the time this way. And I'm going to explain what such a diagram is by taking the old-fashioned world first, not the quantum world, and see what happens. So we take a baseball. It's standing still here. What does it look like on this picture? The space is supposed to be represented this way. Of course, we know space has more dimensions, but I don't have to draw them. I draw one out this way for the other dimension space, and the third one at right angles to both of these and this for the third direction of space. Now, if I represent the baseball by a little slot here, at a given moment, there's the baseball. Later on, the baseball is in the same place. So later on means go along this way. Then later on, the baseball is here. That's the width of the baseball, okay? And later on, the baseball here and so forth. Why did I bother to make it a wide baseball? I don't know. And so here, I could have made it a point baseball and made it easier to draw. The baseball, as a function of time on this diagram, will be represented by that band, all right? Now, if a baseball is moving, okay, it's drifting across the room, what does it look like? This time, I'm going to make a very much smaller baseball, okay? Or you're so far away you can't see the sizing. Let's say it's here now. Later on, it's in another place here, and later on, it's another place here, another place here. So in this world, it'll go so. If it's coasting at a uniform speed, it'll be a straight line. If the baseball goes for a while, hits something and comes back, then it'll go something like this. There was something standing here, right? And it bounces back. Let's say this was a bricks, which were standing still. And that would be a picture of a ball hitting a wall. It goes boink, boink. And I stretch that out this way. Another way to, well, that's, I think, a pretty clear picture. This we represent situations in space-time. So if I were to, in space and time, which I've inadvertently called space-time, which is what everybody calls it. Now, we could say, for instance, that at this particular place, we had a source which emitted a photon at a certain time. This is the time, and this is the place. Then later we can ask if, at this place, a detector at that time would discover a photon. Now, if photons were baseballs, we could say, well, maybe the photon went straight along here, or what have you. But we don't have to say we don't know anything about how it goes, but you know what the answer is going to be. There's going to be an amplitude, that a photon let out of here arrives here. And that amplitude will depend upon the time of this one and the position, and the time of this one and the position. And I'll call this point for just a moment number 1 point, and this is number 2 point. And then we have a thing which is called the amplitude for a photon to go from, well, 2 from 1. And that's one of the great fundamental laws of nature, what that formula is for that. It's a little mathematical formula, and it's very simple. I do not want to bother you with exact mathematical expressions because it won't mean anything. It's easy to describe for those who are more sophisticated. Of course, you realize immediately that the formula for this is going to depend only on the difference of the time and on how far you had to move, the difference of the distances. So it's not so complicated. If the difference of the time is t and the difference of the distances is x, then the answer for this thing is this function, but I don't want to bother you with the mathematical thing. Only know that I can write it down in 1 second, and people who know this magic, this mysterious language, know what that means. So that this formula is extremely simple. It's as elementary as it can be. Oh, it really is as elementary as it can be, as it turns out. If we added a couple of principles, then you can deduce what it has to be, knowing nothing except those principles. The principles are as follows. There's a knowledge of the relation of space and time. The way things depend on time and the way things depend on space are interconnected by a law which is the principle of relativity. And that tells us a great deal, limits the functions a great deal. The second proposition is that the probabilities that you get from this must have the property that if you add up the probability of every possible event, you get 100%. And if you make a wrong formula here, it doesn't check. You know, the probability of everything all added together has to be every possibility, which is 100%. Something's got to happen, in other words. And if you get the wrong formula, it doesn't come out right. You find out that the probability of something happens is 1.5, or -2, or something. So adding relativity and that principle determines this almost completely. Not quite completely. I'll tell you a little more about it in a minute. This function, this depends on these two things. Just for the sake of this discussion, I'll call it D, say. Why D? P, for photon. P is for photon. Between 2 and 1. It's an amplitude of a certain size that depends on the distance between the two. You might at first be surprised because when we were dealing with photons over there, we said that the amplitude was rotating and depended on the time by going around the proportional to the time, depending on the color of the photon. Nothing has been said about the color of the photon over there. Something's wrong. No, it turns out as follows. I will explain it better later. The color of a photon is a result of the source. The source emitting has an amplitude to emit the photon, which is a function of time which is going around. When an amplitude for an event changes with time by simply rotating, not changing its length, but by changing its angle, it corresponds in the real world, I mean the world you're used to, the ordinary world, to be a situation in which the energy of the system is definite. And what we've been talking about before were situations in which the color of the photon, the energy of the photon, was definite. And in those situations, the amplitude is turning around in time. This is, in fact, a result of the source. When we go back to discuss things as a function of time, and all photons are exactly the same, there's only one kind. If the amplitude varies slowly, it appears to his eyes a red photon. If the amplitude varies very rapidly, it's an X-ray. It's all the same. It's just one thing. There's only one kind of a photon when you cut the time. So you see, when you discuss it in time also. So you see that things are getting simpler. To represent that a photon has gone from 1 to 2, we represent that by a wiggly line for no good reason. To represent a photon going from 1 to 2. Now the next thing you have to do, that's the first law of physics. The second law of physics, that's all about optics. That's the entire theory of light. It really is. The part that's not in it is how the light interacts with matter, and I'm coming to that. Next law, that has to do with electrons. Oh, I did cheat a little bit, yes, wait. I told you about polarization of photons, which I've left out here. It also turns out that an electron has 2 states of polarization too, which is sometimes called spin states. And again, I'm going to leave them out because they don't add anything to the ideas. They just add a little complication to the formulas, which you're not going to work with right now anyway. So if you want them, I'll tell you the exact laws, but this is very close. With electrons, we have a similar situation. I just draw the same diagram because I used up my paper and I rolled it away. But if this was time and this was space, we can ask the following thing. If the electron is known to be started here at a position in time which I call 1, it has a certain amplitude to arrive at another position in time, 2. It then will go from 1 to 2, which I'll draw with a straight line to distinguish it from the photon case. And we need a formula for the amplitude for an electron to go to 2 from 1. And that's a different function of the 2. That is a number that depends on the 2. And I'm going to write it down here. No, it turns out a little harder to write that one. It turns out that one involves not only the time and the x, but also another number in the formula. It's more complicated than this. And that other number is a characteristic of the electron. It's called its mass. And I'll tell you in a moment a little more about it. In other words, what this thing really depends on the position 2, the position 1, and the number m, e, the mass of an electron at rest. Mass of an electron. If you put the right number in for that, then that's this thing for electrons. If you put 0 in for that, that's a photon. That's this one. That's D. And as we'll see, for every known particle that we hope in the end, for every point-like particle that behaves like a point, it's got to be this way with some m. You can deduce that alone, this formula for this thing, from relativity and this business about the probabilities adding to 1. The only possible function is a particular one here, which I haven't written down, but I write it symbolically. It's an arrow, which is the amplitude, a complex number, which depends upon the 2 positions, and on some number. In the case of an electron, that's a particular numerical value. Now, it would be nice for me to finish the job and write down the formula for that thing, but I can't make it understandable to you, because unless you have some more enough mathematical background to appreciate Bessel functions. So, but I will tell you a little bit about the function. A special example. A special example, in fact, of the use of such a thing. Suppose that we have a situation where we know at the present moment, time is this way as usual, and space is that way. We know at the given instant that the electron is equal amplitude, exactly the same amplitude, to be everywhere in space. It's equal. Then the question is, with what amplitude will I find it at this particular place later? Answer. It might have been here, and then it would go to there. Or it might have been here, and then it would go to there. Or it might have been here, and then so on and so on. So what you do is you take for each one of these places, for these 2 points, the value of this E, and then for these 2 points, the value of E, and you add them all together, because those are all alternatives. It might be here, and so on. I could write it this way. The amplitude to arrive at point 2 from places 1, which are all different values of x at a particular time t1, we'll call this t1. This is mathematically complicated and frightening. But all I'm saying here is exactly, perhaps I better not say it this way. What you do is you take the amplitude to go from every one of these points to here and calculate it. Add it together. In other words, you add this thing for a given time, but all different places. And then the answer is very simple. The answer is simply an amplitude of a unit length, whose phase, whose angle here, goes around depending on how much time it's been from here to here. Sounds familiar, but it's not a photon. And that rate at which it goes around is very high. It's something like 1 point some odd times 10 to the 20th. That's 130 million oscillations a second. All right? But that time, the speed at which this is going around, if you change this time, is characteristic of the electron and measures its mass. Furthermore, it's pretty obvious that the amplitude to arrive at any other point is exactly the same, because it had all the same amplitudes back here, and if I started with another point here and drew all those arrows and everything, would be the same picture. So the amplitude to arrive everywhere is again the same, but has a different angle. So if the amplitude to be everywhere in space is exactly constant, the amplitude to be everywhere in space stays constant, but changes its angle only. And the rate depends on the mass. A particle whose amplitude is the same to be everywhere in space corresponds to a particle at rest, stationary, in the normal parlance. Also, I told you, when an amplitude is such that all it does, it doesn't change anything except in time by changing the angle, it's a state of constant and fixed energy. An electron at rest has a definite energy, which is called its mc square, I think. It's mass times the speed of light. I've taken the speed of light to be 1 in the units I'm using, so that this just goes around depending on the mass. If I had had a heavier particle, the situation would be the same. I'd put a different number in here, but it'd just be that this amplitude would rotate faster in that case. Anyway, there's a simple example of one of the properties of this function, which is very, very simple. As a matter of fact, if you're clever enough, you can deduce from this, plus the principle of relativity, what that function was, but you're not that clever, so we'll let it go. But I'm just trying to emphasize that the particular function, although I haven't written it down exactly, is as simple almost as it can be. Finally, there's one more rule, and that is that if an electron comes to a point at the same with a photon, they come together at a point, an electron and a photon, that an electron can go off from there. There's possible to have a junction. And there's an amplitude that there's a junction. The amplitude that a photon is absorbed by the electron, let's say. Or whatever kind of a junction you've got. We can talk about what the junctions mean. But every time you see a junction, you get an amplitude. That amplitude is given by a formula. C is equal to 0.08542, and so on. A number, just a number. 100. Physicists like to remember this number in the form 1 over c squared. And they write c squared is 137.03599 plus or minus 3, and that's the result of an experiment. That's a magical number, a mysterious number. Good theoretical physicists put that at the top of their bed at night and dream if they can figure out why that's the right number. The fact that we have no idea where that number comes from, and it's one of the mysteries and incompletenesses of the theory, because it would be nice to get that number out of something. It's done by experiment. I'll discuss that problem in much more detail in the next lecture when I talk about the limitations or the incompletenesses of the theory, and also other particles in nature and all the other problems of physics more complete, not just electrodynamics. Well, now we see we have just these parts, and I would like to discuss calculating the amplitude for a number of different events so that you can see what's involved. So the first example will be this. Suppose that I have two electrons, again time this way, space this way, and so on. I have an electron, I know it states at position 1 and time, the position time 1, marked 1 here, and another one at 2. And I would like to know whether at a later time I will find one electron here, well, let's not put it in the same place, and another electron, say, there. All right? So one electron should be at 3 and the other at 4. Now, to find out how to do it, the first thing I do is I suppose that the electron number 1 went to 3 and the electron number 2 went to 4. So I draw a picture like that, and I read the picture mathematically as follows, that the amplitude for this event is the product, as we talked, because these are two independent things. There's one factor, which is the amplitude that this gets from here to here, which is just that E thing, which is some arrow. And there's an amplitude to get from here to here. If I were writing it mathematically, I'd write E31 times E42. But what I would mean is I'd get from the formula the size of the arrow here, and then I'd multiply it by the size for this arrow, and that would be the answer. But that's not the complete and exact answer, because there's another possibility. So I must consider other possibilities that can occur. Another possibility is that it was this electron that went to there. I'm just drawing the same picture over again, but making a recombination. This is 1, this is 2, this is 3 and 4, and the amplitude for this one would be E3 from 2, E4 from 1. And from what you've learned last time about photons, if it can happen in two different ways, you add the amplitude. But for electrons, there's a different rule. When it can happen in two different ways for electrons, you subtract the amplitude. This subtraction has a very profound and remarkable influence on the behavior of electrons, and is the reason why electrons behave more like particles experimentally than like waves when they were first found. I'll come back to that in a little while. Let's forget this for a while and let's talk about just situations like this, that somehow you know it's the same electron going here. This subtraction is extremely interesting. But I'm going to come back to that because I want to concentrate on something else. Well, there's another way that the first thing can happen beside that exchange, and that's this. It could be, here's the particle at 1, and here's the particle at 2, and the particle that goes to 3, and the other one's going to go to 4. Now, I had them going directly. That was the first thing. But you must add an amplitude for every possibility, so we have to keep on going and adding something. It could be this. Number 1 could go to some place in time and space, which I'll call position time 5. The electron can go to here. Yeah. And then go from 5 to 3 and make a junction here by emitting a photon. And the other one go to the other point where the other end of the photon is 6 and go to 4. Now, if you're brave enough, I'm going to write the amplitude for this thing in a high-class mathematical fashion, and you'll be able to follow it. The answer to this amplitude for this contribution here is the following. E35, E51 times E46 times E462 times, anybody got another guess what else is in it? D56. That's a P, photon, 5 to 6. And forgot something, C times C. How's it work? If I haven't made a mistake here, there's the amplitude that the electron goes from 1 to 5. And then an amplitude, the electron goes from 5 to 3. Times an amplitude, that's a junction. That's a C. Likewise here. In addition, there must be some amplitude that the photon that's been liberated at this junction has gone from 5 to 6. You put that in too. You multiply all these together by those rules. I know it's getting complicated. We're piling a lot of stuff together. But it's like playing checkers. There's a few rules, and you just have to use them a lot. You got triple jumps, but they're nothing but single jumps repeated. So it's like each of the thing is simple. It's just repeated and repeated. So we calculate this thing and add it, that amplitude with all its arrows, and multiply to that one up there. Let's forget the other case for a minute. Add it to that and be improved accuracy. It's not quite finished yet. Why? Because, of course, you could have something like this. And so on. I mean, there's all kinds of wonderful things. We'll come to all kinds of wonderful things in a minute. You got 2 of them going across and so on. Well, this is a hopeless task. And you got to keep adding and adding and adding and never get finished. But we're going to get a good luck. Good luck. You see, this amplitude has a number of factors in it, but it also has C times C. And C times C is a relatively small number of the order of 1%. And as it turns out, the contributions from a picture like this under ordinary circumstances is about 1% of the contribution of this. The reason I say that under ordinary circumstances, it can happen that you've got a situation where this one is adding a lot of cases and a particular picture cancels out by interference, and then something that's 1% smaller is the whole thing, and so on. Forgetting all about that, each time you add an extra photon, you add a C squared, it makes it 1%. So therefore, if I make a picture like that, it's 1% of this one, which is 1% of that one. So by the time I got down to this one, I got things correct to 1 in 10,000. And then I would get to the lazy, putting 3 of these darn things across. So then I got to 1 part in a million, and that's why we can calculate so accurately, because we can do 1, 2, 3. Never can get to 4. It's too complicated. And there's another thing I forgot to say, and that is that where's 5 and where's 6, you're sitting there asking. Anywhere. Yes, anywhere. Those are all possibilities, and those are alternatives. 5 might be here and 6 here, and you have to take that, then you have to put them somewhere else and add them and add it and add it for all different places that 5 and 6 can be. All right? So what I mean to do is to add this together for all places that 5 can be and all places that 6 can be. I mean by its places, positions in space and in time. If 6 is later than 5, you're inclined to say the photon went from 5 to 6. If 5 is later than 6, that is, if I got this around that way, you would say the photon went from 6 to 5. In other words, in one case, this emitted a photon which the other one absorbed, or vice versa, this can emit a photon that absorbs. But it's a funny thing in relativity, it's very difficult to say when two things are nearly at the same time, which is ahead. And this whole business of trying to decide when they're nearly at the same time, which one is emitting the photon and which one is absorbing the photon is in irrelevancy. This function for photons is large when the distance is big, only when these two are at such an angle that you usually can get there at the speed of light. You usually think light goes at the speed of light. You used to think light went in a straight line. Light goes on many different lines, and the result is it looks like a straight line to a gross sense. Light goes at different possible speeds, at different kinds of angles here, and the superposition when the distances are big is that it gives only a result when the speed is at the speed c. So I have now finished telling you, well, one thing I cheated a little bit in the fact that I left out the polarizations. And this junction thing has a whole lot of different numbers, depending upon different polarization cases. It could be one kind, another kind, another kind, different combinations of polarization cases here. And those numbers are those are a little 1, aside from this factor. It's either a 1 or a -1, or sometimes a pure vertical thing like that, or sometimes a pure thing like that. Very, very, very simple. So if I'm going to leave out polarization altogether, I'm not giving you a wrong impression that the junction is just C, this number, times 1. It's not exactly 1. Sometimes it's -1. It's a little different, but that's for different polarization cases. But I don't want to deal with that any further. From that, all the phenomena of nature occur, result. For instance, you know that the light can be scattered. It comes from the sun and is scattered by atoms in the sky, so you see blue sky. How does it work? If we have an electron, well, let me go in a slightly different order. I'm going to come back to that case. I stepped on my own cord that time and it choked me. I have now recovered enough to continue. In order to understand the behavior of electrons in atoms, we have to add one other feature, and that is the nucleus. The nucleus is not completely understood, and I will not give you the correct laws for the behavior of nuclei if I could. I wouldn't waste any more time lecturing here, but I would publish it immediately as it is unknown. These functions that we know so well must be the right functions when things behave like points and have no internal structure. And it has turned out experimentally that the electron and the photon have no internal structure to as small as we've been able to look so far experimentally, and that is to distances which is 10 to the minus 15 centimeters, approximately 10 million, 1/10 millionth of the size of an atom. Small enough. So it looks like a point. But the nucleus doesn't look like a point. But for many, many phenomena in atoms, you can approximate by supposing the nucleus is a point. And insofar as you can approximate the nucleus as a point, you can do the same trick with a nucleus, but put the mass of the nucleus there. That is only approximate. For the electron, this is right. For the nucleus, it's approximate. So if I want to describe a hydrogen atom, I have to represent the nucleus, so I'm going to represent nuclei by lines, thicker lines, double lines, like this. This is an electron, that's a photon, and this is a nucleus. A nucleus, let's say to take a hydrogen atom, the nucleus is just a plain proton. And it looks fat because we don't understand it inside there. But the electron is nice and thin, and it goes along, and nucleus might emit a photon